Okay, I'm going to talk to you a bit now about my project, which was a comparative life cycle analysis of wave and tidal energy devices. So, as we probably know, wave and tidal are sort of two parts of what's collectively known as marine energy, which is basically energy from the marine environment in any form. So there's lots of sort of different concepts being tested and things at the moment. You see on the left-hand side of that one there, that's a device that, as the waves sort of crash up on it, it pushes a column of air through a turbine, and that generates electricity. You can see here, this is a wave device as well. Sort of as the waves move, it flexes, and joints between the cylinders there, they generate electricity. This one just here is a tidal stream device. So rather than generating electricity from the waves, that works as the tides move in and out. They're generally located in sort of narrow channels at the end of locks and that sort of thing. As the tide moves in and out, it turns underwater turbines, similar to sort of wind turbines basically, and the electricity is generated from those. And that one at the bottom there is another wave device. It's sort of quite a common design. It's basically a solid bit mounted on the bottom of the sea and then a flap attached to it, which moves from side to side as the waves move over it. So looking at sort of wave and tidal devices side by side, there's some obvious differences in that they get the energy from the wave and tides. Waves are caused by the wind and are unpredictable, whereas tides are very predictable, which is sort of a critical consideration. Tides can be predicted many years in advance, whereas the waves, obviously, we don't really know what's going to happen. This means, in terms of sort of looking to extract a reasonable amount of energy from these things, if you're relying on waves to generate a reasonable amount of energy, you need to have a backup in case there aren't any waves. Whereas obviously with the predictability of the tides, you don't need that so much, so that's a consideration. But that's not what I looked at in this study. I looked at the life cycle analysis of these two specific devices. That one on the left, they're both ones I had on the previous slide. That's called the Oyster, the device on the left, which moves from side to side in the waves. And this is the CGen underwater turbine. Both of these, you can see that they're envisaged in the future to be installed in arrays. But both of them at this stage have been installed as sort of test devices, just single ones. This is sort of the aim of the project, to conduct a comparative life cycle analysis. I conducted the analysis for the wave device, the Oyster device, and the CGen tidal work was based on, or in fact taken entirely from, a previous study that somebody else had done. So quickly, the tidal device, the CGen device, it's a 1.2 megawatt rated machine installed in Northern Ireland as a sort of test device. And from the study that was carried out on it, the life cycle analysis came back with a energy payback and CO2 payback. You can see there 14 and 8 months. So compared to those, I did the LCA on the Oyster device. So you can see there I described how the flap moves in the motion of the waves. That pushes water through a closed system, so through hydraulic rams, which you can just about see on the picture there, through a underwater pipeline back to a hydroelectric power plant, which you can see the actual version of here, where it drives a Pelton wheel, which drives a generator and generates electricity, which is then exported to the grid. The rated power of this device is slightly smaller than that of the CGen device, but they're both sort of similar level of development, which is why I decided to compare these two. So looking at the Oyster device to do the life cycle assessment, materials transport, installation, maintenance and decommissioning and recycling are generally sort of users of energy and carbon emissions, and then obviously the output from the device is going to be a saver of carbon emissions and generator of electricity. So that's the kind of comparison I did. So I'll just quickly kind of go through now what I looked at for each of those sort of blue boxes and how I assessed the emissions and energy use in those. Materials, I sort of very quickly worked out what it was made of, how much of each thing there was, using ICE data from the University of Bath, worked out the embodied carbon and energy in each bit of that. There's a lot of work in that, but just very quickly, it weighs about 150 tons and there's about 300 plus tons of CO2 involved in that. is just an example. That's the ICE data that I mentioned from the University of Bath. So that's quite well sort of validated embodied energy and carbon data. So I was able to use, and that's just a sort of screen grab quickly from the spreadsheet that I used to calculate all this stuff. So moving on to the transport. The device was installed in Orkney, so obviously there's a fair bit of transport required to get there. They didn't build it on Orkney. It was built in various parts in various places. So I calculated all the various emissions from the enormous trucks and things like that, and the ferries that they used to get it from where it was manufactured to the site, and all assembled on site. And the installation as well. The installation was sort of one of the biggest, most expensive and most energy and carbon intensive processes of the whole job. It emitted over nearly 400 tonnes of CO2 to install the device. These are sort of examples of the processes that were gone through to do that, and then within each one of those I had a number of sub-processes. So calculating emissions for the drilling of pipelines from jack-up vessels and things like that. As you can see, that's quite an expensive process as well, the installation. I also calculated the cost implications for the Oyster device, but this wasn't done for the Tidal device. So that was just sort of while I was working out the other stuff, I included that. Maintenance was probably one of the most unknown areas that I worked the emissions out for. At the moment it's based on 4 people travelling by car 3 times a year. Whether that's correct or not, I don't know. We're hoping to get in touch with the manufacturers. They weren't able to give me any data at the beginning of the project, but hopefully when we send them the paper and it's generally positive, they might be able to give us some more information. So this might be updated. But maintenance, even modifying these figures to make them quite high emissions, maintenance was a relatively small part of the whole emissions. Decommissioning and recycling. I followed what was done on the CGen study for this one, so that's basically saying that the decommissioning of the device is a reversal of the reversible processes involved in the installation. So obviously you can't undrill a hole, but things like the bolting of things onto piles and things like that, they would just reverse those processes. It was about 40% of the processes that were done in installation were reversed for decommissioning. And you can see the recycling, it's assuming that all the recyclable material is removed and is reused in other projects instead of primary material. And that saves those amounts of energy and carbon there, but due to the cost of all the decommissioning, there is actually a net overall fairly large cost to the recycling. Okay, so that was sort of inputs. The output of the device. This matrix on the left is sort of equivalent to a power curve for a wind turbine, except that it's not a curve because there's more variables. But basically combining these two, and this is a sort of frequency of occurrence of certain heights of waves recorded on the Orkney site where it was installed. So using these two, I was able to work out the estimated power output annually at about 173 kilowatts from the 315 rated power, which, combining all these sort of figures that I've said up to now together, this is basically the output of the life cycle analysis for the Oyster wave device. Yeah, fairly sort of self-explanatory. So you can see the lifetime figures here. Green is good, red is bad. So there's a lifetime energy generation. This is assuming a 15-year lifetime at present. Lifetime energy generation of 76 terajoules. CO2, that's a CO2 offset or saving compared to electricity generated from a gas-fired power station. But at present there is a lifetime cost of £1.1 million. A large part of that cost does come from the installation, which for this sort of test device was very, I don't know what the most appropriate word to use was. They tried a few different ways and most of them didn't work. So it would cost a lot less now they know how to do it in the future. So that cost is likely to be to fall. So comparing the Oyster wave results that I got to the CGen results from the previous study, using the data that they generated, which is in terms of energy and carbon intensities at the top here, you can see the Oyster and the CGen device are fairly close together and roughly comparable to wind turbine figures. Those wind turbine figures are from papers issued by Vestas on large wind turbine installations. So as that's a sort of fairly large installations of fairly well-developed technology, I think those figures are probably quite good, quite favourable for the wave and tidal device there, considering this stage of development. And also the energy and carbon payback periods, very close for the wave and tidal devices. Yeah, further work. So yeah, as I said, they're both sort of, I think, seem fairly good at the moment. There's a lot of potential for development, particularly with the installation, and as if they are installed in arrays as planned, and also both of the devices are considered as sort of test devices for bigger machines to be developed, so the costs are probably likely to reduce per kilowatt, again, from that. And there are other issues that I haven't looked at in this, obviously due to like survivability and things in the sea of these devices, and the issue of the backup if wave machines are to be used. But yeah, that's about it for now. And does anybody have any questions?